Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A quick update on our deep learning study group. As you know, we're huge fans of the Fast.ai courses, and we recently had our second group of deep learning learners complete the Fast.ai Deep Learning for Coders course back in December. I'm excited to announce that we'll be hosting our third group of students taking the Part 1 course starting this Saturday morning, February 2nd. This study group will run 7 weeks, finishing just in time for participants to jump right into the Deep Learning for Coders Part 2 course, which is set to start in mid-March. For details on the study groups or to get registered, visit twimlai.com/meetup. While at NeurIPS this past December, I had the pleasure of attending the second annual Black in AI workshop and dinner, which brings in participants from all over the world to showcase their research, share experiences, and support one another. I was fortunate enough to spend the day at the workshop, and I'm excited to share with you over the course of this month conversations with just a few of the great members of this community. To keep up with the series, visit twimlai.com/blackinai19. To get this series kicked off, we're joined by Randi Williams, PhD student at the MIT Media Lab. At the Black in AI workshop, Randi presented her research on Popbots, an early childhood AI curriculum, which is geared toward teaching preschoolers the fundamentals of artificial intelligence. In our conversation, we discussed the origins of the project, the 3 AI concepts that are taught in the program, and the goals that Randi hopes to accomplish with her work. This was a fun conversation. It was super thought-provoking. Enjoy. All right, everyone, I am on the line with Randi Williams. Randi is a PhD student at the MIT Media Lab. Randi, welcome to This Week in Machine Learning and AI.
Hi, thank you, Sam, for inviting me. I'm happy to be here to talk to everyone about my work.
Absolutely. So we had an opportunity to meet at NeurIPS recently. In fact, You presented at the Black in AI workshop there. And I was really fascinated by the work you're doing in teaching preschool children about artificial intelligence. What sparked your interest in doing that and teaching young children about AI?
Thanks. The workshop was definitely incredible, and I was happy to share my work with the people there. So I am a PhD student at the Media Lab. I've been working on this project for about 3 years. And when it started, it wasn't about AI, and it wasn't necessarily about preschool children either. It was about computational thinking and how do we help students who might not have access to fancy robotic toolkits or to teachers. How do we help them start to learn about these things? So how do we spread the influence of the whole craze about CS to different populations? So I'm from Prince George's County, Maryland, but my family's from Baltimore, and I went to school in Baltimore. And while I was in undergrad, I spent a lot of time working with inner city children, and doing maker spaces, Arduino workshops, that kind of thing. And what was really awesome about it was how engaged the students were with learning these different things. But it also made me a bit sad that so many of my classmates in school, they were like, oh yeah, I've been programming since I was 7, and these students, they were high schoolers and they're just getting started with this. So I just felt really strongly that there needs to be more done to help everyone have a chance to learn about these things early on. And what was really difficult in Baltimore was that there just weren't a lot of teachers, there weren't a lot of people who knew about the field to come and teach the kids and share their expertise. So within the group that I started working in the MIT Media Lab, it's called the Personal Robots Group, and my professor is Cynthia Brazil. And she's really passionate about how AI and robotics can help us flourish as human beings. And so a lot of our work has been about education and how robots play a role in that. So I started out just building a robot that could help children learn how to program and sort of be the fun, interactive learning companion to help them, figure things out and push them to solve new problems and things like that. So in the absence of a trained teacher, how can a robot help children learn about these kinds of things? And it was really fun. I just started thinking about, like, so what makes the most sense? Having some experience in Baltimore, I was like, well, no one's going to go buy a $200 robot to do this. So how do we make something less expensive? So the Popbots project that I'm working on is mostly based around a mobile phone. So the mobile phone is the intelligent robot that children program. And then I was also thinking, well, how do we break away from computer sciences, solving mazes or doing puzzles, and really open it up to different interests that students might have. So the robot, can become a character. You can make it look like whatever you want. It can control the lights around your room and things like that. So it's sort of like opening doors for, art and theater and music even. And then somewhere along the way, I was having a conversation with Cynthia one day about the project and the direction. And she was like, Randi, your work is great, but you should really think about AI, because AI is the next big thing. And no one's really doing like AI education. And, as a student, I'm like, okay, well, I've taken AI classes in college. I don't really know how I'm going to teach children AI, but yeah, sure, let's go ahead and try it. So I quickly pivoted, and how did I end up with preschool children? Well, there were a lot of like robot kits for like the 7 to 10-year-old age. And I guess enjoy not sleeping and like solving really crazy problems. So I was like, I'm going to go like right below that. I'm going to do the 5 to 7-year-olds. And it worked out, I guess. So we have a 5 to 7-year-old preschool AI toolkit that I'm working on.
That's awesome.
Yeah.
That's awesome. So is the Media Lab, is that its own department, or are you affiliated with a computer science or robotics department? And kind of what I'm also curious about here is, have you also received any formal training in education? And how do you kind of think about the interdisciplinary nature of your project?
Yeah, so the Media Lab is this weird, crazy place. I work in a robotics lab. The people next to me, they do devices that go underneath your skin to help monitor your health. And the people on the other side of me do neurobiology. So it's a department with pretty much anyone who has a crazy idea that doesn't fit into a like normal science or engineering department. That's the place that you go to do the work. So as a result, I get to do this project that's very interdisciplinary. I get to think about art. I get to go to schools and do education work. I get to build robots. And I also have lots of resources around the lab where people do all of these things and can sort of help contribute to the project and help me grow my ideas. So I don't actually have formal training in education. However, a lot of the work that I'm doing is built on this program called Scratch. So Scratch is this website where children ages 7 and up can go and learn about CS. And it was, so currently the leader of the lab is Mitchell Resnick, but I believe it was started by like Seymour Papert, Logo turtles. If you don't know what that is, it's these turtles where Seymour Papert back in the 60s was like, all kids should know how to program and all kids should be able to do this. And this is when like computers weren't even very popular, so everyone was like, dude, you're crazy. But he's like, yeah, I'm going to do it. And so he started building this programming language for children. And generations later, there's this online portal where literally millions of children all over the world are learning how to program. So even though I didn't have the background, the CS education background to know how to do it, I got to work with Mitch and I took his class and I learned from his students and can start to pull those things in. I also didn't necessarily have a background in robotics. I did computer engineering in undergrad, but mostly like building little devices, not things that were like big and interacted with people. So I learned a lot from my group. And then everyone at the Media Lab, they're kind of just, like artists. So I'm not an artist, I'm an engineer, but I became an artist and was able to pull that in. So really, what's awesome about interdisciplinary work is that you get to pull in from all of these different fields. Talking to developmental psychologists, can kids understand AI? Are they ready to do that yet? What are the right ways to translate the information so that it makes sense to them? I've really actually been inspired by all the people who I've gotten to work with.
So when we think about teaching AI to preschool kids, obviously we're not trying to teach gradient descent algorithm or anything like
Yes.
that. Like, how do you the, how do you kind of break down, or maybe take it from the other direction? What are your goals in trying to teach AI to children at this age level?
Yeah, I would say my primary goal is to give children agency in the world around them. So before I even, put out the toolkit and started like actually testing with children and building things, I did a whole series of studies with other people in my group around what do children think about AI. So we would have them interact with toys. If you look at kids' toys now, they're like amazing. They're really cool. So they have like these little robot things called Cosmo, which like they move around and they can play games against you, and they're super cute and you can program them and stuff too. But, it's like real AI that is being marketed to children. Then there's all this controversy about this Barbie doll, Hello Barbie, that could talk to you. And every kid in the world, I think, has had a conversation with Siri or Alexa. Not every kid in the world, but quite a few have. So it's interesting to see how in our time, computers were just kind of like coming to be, and the internet was just coming to be. And children are growing up in a world now where it's like, yeah, AI is kind of a thing. Like it's normal to see that. So I was like, okay, so when a child interacts with this thing that's not alive, not a human, but can talk to them and seems kind of smart, what are they thinking? What's going on in their head? And oftentimes they're like kind of just figuring it out. They're like, okay, it talks to me. Like, let's poke it. Let's see if it can answer questions about dinosaurs or sloths, or does it know what's in the grocery store down the street? Things like that. And then they're like, well, can I break it? Hey, do you want this apple? Or, asking these kinds of things to computers and just to see what it will say. Or, hey, do you have a boyfriend? Do you have a girlfriend? Funny things like that. But even more so, they kind of didn't really understand how it worked. And to me, that's like an opportunity and a challenge for today, because we don't really want children to have toys that they can't pick apart and understand. They're like, Alexa won't answer my question. Does she not like me? And it's like, no, Alexa's NLP algorithm just isn't programmed for young children's voices because it was made by adults who thought only adults would be using it. So, that's what's going on. But if you say that to a kid, they'll look at you like, what are you saying? I have no idea what's going on. So the goals of the curriculum are really to help children break those kinds of ideas down. Like, oh, Alexa isn't working because Alexa was trained a certain way. And if you try and have Alexa do things outside of the way that she was trained, then she's not going to get it. Like, that's kind of the right level that I think any child should have.
It makes me think a little bit of a couple of examples. One that comes to mind is when children who are raised on iPads see magazines and start tapping at the magazine,
right,
wanting it to do something. Or the other example that comes to mind is knowing how to really effectively search Google. It's a powerful skill, but both of these things I think illustrate like mental models that are created over time about this thing that you're interacting with. That, in the case of an iPad, it's just like this piece of glass, but you kind of develop this model about like how, flat things work, I guess. Or, in the case of a search box, like, how you can really effectively use, this world that's behind the search box. Is part of your work here trying to shift the mental model that kids have about AI?
I actually really love that framing, and I might have to use that in the future. Like what are children's mental models about AI? Yeah, so that is literally what I'm doing. So a part of the actual Popbots study that I did, so I have children interact with the AI, and not just interact with it, I also have them like building algorithms from scratch. Not the whole thing, like they're not writing the programming, but pretty much they have a lot of control over the way the algorithm works. So we do that. And at the end of the day, they have this finished AI product that seems intelligent. And before and after they're learning about AI, I ask them, what do you think about this thing that's in front of you? Do you think it's alive? Is it a person? Is it a toy? Is it an adult? Is it a child? Is it smarter than you? Are you smarter than it? And I'm asking all these questions because I expect a mental model change to happen when children are learning about AI. And I'm wondering, how can we make sure that, there's so many privacy and security, like safety concerns around having something that's always recording you in the house. So what are children's mental models, and how does learning about AI impact that? How does it change the way that they want to interact with these things in the future?
And what were some of the results you saw in these before and after surveys?
Mostly very strange things. So before, well, the studies that I did 2 years ago, I interviewed 4 to 10-year-olds about AI, and the older kids, the 8 to 10-year-olds, they were solid. They knew exactly what they thought about AI. And, they're like, it's not a person, it's not quite a toy, it's somewhere in the middle. They knew what they were doing. But the younger children, they kept telling me, I don't know. And I was getting frustrated, as a researcher, because I'm like, I don't know, it's not going to get me a paper accepted into a conference. And so what I found before was pretty much the same. Children were like, I'm not really sure what this thing is. We're all over the place. People saying yes, people saying no, people saying, oh, it said my name, so I guess it's pretty smart. Or it didn't say my name, or it doesn't know my favorite song about the train, so it's not smart. Just things that were very hard to understand, which is interesting because parents are also looking at this and they're like, I'm not sure what my child thinks about Alexa. They keep calling it their best friend. So, what is this relationship? But afterwards, there were some interesting differences. So I split my age grouping into pre-K and kindergarten children. And so after they had learned about AI, the pre-K children were like, oh, now I understand it. So yeah, I would say this thing's pretty smart. And the kindergarten children were oh, I don't think it's smart anymore. I thought it was smart before, but now that I get how it works, it's nope. I'm okay. And then I also created assessments, very simple multiple choice questions to ask how much did children really understand about the activities that I had given them, and how much were they understanding about the AI concepts. So the ones who did the best on the AI concepts were now that I've played with this thing, I'm yeah, it's kind of like a person. It thinks sometimes in ways that I think. And yeah, it could be smarter than me too. It could learn and it can get better and better. But interestingly, the children who didn't understand the AI activities very well were the opposite. They're nope, not smarter than me. It's just a toy. It's fun, but it doesn't seem to be as alive or as human to me. And so I'm still undecided about what conclusions I want to draw from that. But I definitely think it's interesting that there is a big difference. The children who understood AI versus the children who didn't understand AI saw the technology in very different ways. So at the very least, it sounds like teaching children about AI does cause something interesting to happen. Something interesting and hopefully not negative. So it seems like a good motivator to continue with the work and to continue to explore this.
I can't help but think that teaching adults about AI would have the same positive effects. You think about kind of some of the mass media coverage of AI and some of the, hysterias that you read about, they often kind of belie this just lack of understanding. And have you thought about creating an adult version of your curriculum?
So I haven't thought about it myself, but sort of, even to discuss what you were mentioning about the more that people understand, the less scared they might be. I think that the way that, AI conversations are just playing out in society right now, it's kind of a little bit of both. So there are some people, I guess, like myself and people in my lab who are look at AI, look at how much good it can do. We can use it to build, this good thing, that good thing, this good thing. And I would say that we're experts. But then there are also people who are extremely wary of AI. So they're they see this technology coming and they see all the negative ways that it can be used. And they're cautious to completely repulsed by it. No, even if AI can do good things, we shouldn't build it because in the wrong hands, it can just be too powerful and too destructive. And so I think that any adult education AI thing would probably have an interesting time trying to wrestle with that, not trying to push people in any particular direction, but to let them come up with their own interpretation of how they think the technology should continue.
Mm-hmm. Yeah, no, that's a really interesting point. I definitely get where you're coming from. It's almost like the thing that you're afraid of isn't really the thing you should be afraid of.
That's true.
You know
Yeah.
what I mean? It's not that there's nothing to be afraid of, or not even afraid, but worried about. There are genuine concerns, but it's not necessarily kind of this Terminator scenario in the next 5 years.
I can tell you as a roboticist, there will be no Terminators anytime soon because robots love to break. Like, they're just not going to work out. Now, if there could be what is the movie? Her, like the thing where it's like all online, like that's a bit more likely. But I'll let you guys know if Terminators are ever going to come.
Let's maybe talk about the curriculum that you developed as part of Popbots. What are the core AI concepts that you're trying to teach these children?
So the 3 that I started with were knowledge-based expert systems, supervised machine learning, and generative AI. And I started with these because they seem to be the most relevant to what children were experiencing. So a lot of their simple toys were using these, kinds of concepts in them, and I could easily make connections between when your toy does this is what's happening underneath it. And to me, that seemed like the most important things to teach children at first. Knowledge-based systems.
Let's go through each of those, and maybe you can provide an example of the way a child might experience that in their kind of everyday toys, and how you introduce that in the curriculum.
Knowledge-based systems, or rule-based expert systems, or expert systems, they have multiple names, often come up in natural language processing. Now, a lot of NLP also uses, deep learning, but in the past, back in the good old days, it came up a lot in natural language processing, as well as medical diagnosis, and even the video game characters that, aren't the main characters, but the ones that, I don't know, if you play a lot of RPG games when you're battling the random townsmen, like those kinds of characters were all controlled by knowledge-based expert systems or rule-based systems. And so it was easy to, talk to children about. It's like, oh, when you're playing tic-tac-toe against your smart computer, or when you're doing that video game, or when you're talking to Alexa, there's probably a bit of this going on underneath. And the way that we did the activity was we played rock, paper, scissors. So rock, paper, scissors, you need knowledge. Like, there are rules, which is, rock beats scissors, paper beats rock, etc. And so children would literally program these rules into the robot. All of the interfaces are completely picture-based because I was working with children who were so young that they couldn't read. So it was an interesting design challenge to say, okay, powerful AI, absolutely no words whatsoever, and like no math and stuff like that. So children pretty much put like pictures of a paper hand and then an like greater than sign and then a rock, which means paper beats rock. And so they put in all the rules, and now the robot has its knowledge base, and it can use that to make decisions about what to play. So when the child's actually playing against the robot, then the robot will kind of keep track of their moves, and it'll use that to say, oh, well, I think that you're going to play paper next, and you told me that scissors beats paper, so I'm going to play scissors. And then it's revealed, did the child actually play paper? And a lot of times, after a couple rounds of the game, the robot's pretty good at guessing. And they're like, oh my God, the robot got so smart. But what's really cool about that is it didn't start off smart. It actually starts off losing a lot. And as it keeps going, it gets smarter. So children start to see how this intelligence didn't just appear. It was learned over time. Also, the children gave the robot the rules to the game. So the children actually played a part in helping the robot become intelligent. What's even more funny is that the kids will be like, I'm going to cheat. And they'll like switch all the rules around backwards. And the robot will be like, well, I guess that paper beats scissors. So does that mean that I win? And the child's like laughing their head off, like, ha ha ha, I tricked you. But that's actually an interesting point because, in expert-based rule systems, one of the ethical issues is what if the rule that you're teaching isn't correct? So children even get to explore that idea, like, okay, if I have a car that's driving by itself and I teach it the wrong rules, what happens? And you can see like this look of realization, like, move over the child's face, and they're like, oh my God, that would be so bad. And I'm like, yes, like you're understanding, like, the impact, the real world impact of AI. And then also, children will teach the robot how to react to winning, losing, and getting a tie. So, like the robot can be a sore winner, and like every time it wins, it's like, haha, I win, you lose. And like it makes this farting sound. So that's like one iteration, or you can have it win humbly. And it's like, oh, that was a good game. So children are also, it's kindergarten, it's preschool. Children also need to have some way that, social interaction, social learning is coming into this as well. So that's a part of it too.
I'm curious in this first part, the rules-based systems, when the child was programming the robot, teaching the robot how to respond via these rules, were you also introducing some notion of probabilistic systems or responses?
So in the sense that the robot was learning over time what the child was most likely to do next, yes. It was a little bit tricky because probability doesn't come up for a while in like early education, but we would make these rule trackers, or these game trackers rather, where the children would write down, what moves they put. And the robot would say, well, I think you're going to put paper next because you put paper like 3 times out of the 5 times that we just played. And the child can look back at what they did and they can start to see, oh yeah, like 1, 2, 3, like those are the times that I picked paper. So yeah,
that's the sense in which I envisioned it. Yeah.
Yeah. It was like, it's not like super deep, but yeah, that's about how far we can go with it.
But you kind of raised that as that was made explicit in the curriculum, thinking about, these, percentages or frequency types of numbers.
Yeah, absolutely. And the entire time the robot is like saying these things, it's pointing out what its knowledge is and it's explaining why it's making decisions so that the child can understand it. And I think my hope is that, when they get older, if they have another AI class, they can revisit these ideas and actually learn about probability and it all starts to make sense. So like even reinforcing those ideas later.
And so just a point of clarification, you are referring back to this idea of a robot. Is this an entirely software-based robot just on the smartphone, or is there a hardware component as well?
Yes, I should have explained that. So the robot is a mobile phone with this social robot technology that we developed in our lab. So it can talk. It has all these really cute, fun animations. It can listen to you. It has a camera. But around it, I've built a Lego body. So there's 2 different bodies that I'm working on now. One uses Lego Redo, which is like this $200 motor kit, and you can use normal Legos, and then you can add these motors to it. So now the robot can move and dance, but because it's Lego, you can change the way that it looks. So sometimes it's a car. Some children really wanted to play with one that's spun around, so they can sort of have total control over the way that their robot is. So they're programming it, they're building it, like all of it is brought down to the child's level. And then the other one I mentioned is Arduino. So now I'm like, thinking about, slightly older kids and even more fun things to build. So I'm building an Arduino platform for it too.
So then back to these concepts, we just talked about the rules-based types of systems. You mentioned supervised machine learning as well?
Yeah. So supervised machine learning comes up in YouTube Kids, which surprisingly a lot of children were interacting with. So I would ask them, how does YouTube know which movie you want to watch next? And they're like, oh, well, it just, it just picks whatever is random. And I'm like, no, it's not random. It usually picks things that are kind of like the video you just watched. And they're like, oh, yeah, I guess you're right. And so we can talk about supervised machine learning. So that's when you label some things, for example, as good and bad. So in the case of YouTube Kids, children are labeling things as things that I want to watch by watching it. And then they can also give extra feedback, thumbs up, thumbs down, so that YouTube's algorithm can learn better. But it's often used for like recommender systems. So it can be YouTube, it can be Netflix. Children don't have email yet, but sometimes they can kind of get what I mean if I throw that in there. But for children, what we do is we sort foods into healthy and unhealthy groups. So rock, paper, scissors is nice because it has 3 roles. But if you want to teach a robot about which foods are healthy and unhealthy, I have children think about like how many foods are there? Like how many foods would you have to teach the robot about? And after they kind of like hit to 30, they max out and they're like, oh my God, that's so many foods. So I'm like, okay, there's a better way. We can give the robot a few examples and it can learn to make guesses on its own. So sort of on the back end, something I do beforehand, the robot has this database where it has like the color of foods, what food group it's in, how much sugar it has, all of these different features. And then it's going to use a k-nearest neighbors algorithm to sort of say, well, this food has this many features similar to this other food. So maybe these two are nearest neighbors as opposed to this other food. So a good example is like bananas would be more similar to lemons than chocolate. So what I have children do, they have this like list of 20 foods, and I say, we're going to label 2 of them. So they label, either both of them good or both of them bad. They let them pick whatever food they want. And then we're saying, okay, now let's ask the robot to guess like whether this food is healthy or not. And so they start to see like, okay, if I tell the robot that strawberries and tomatoes are healthy, and then I ask about chocolate, it's going to think chocolate's healthy too, because I haven't given it any bad examples, so I have to do better. I'm like, okay, let's teach the robot that chocolate is not healthy. So now we have strawberries and tomatoes in the good, chocolate in the bad. Let's ask it about ice cream. And the robot can say, oh, well, ice cream is probably closer to chocolate than it is to the other things because they both, are in the sweet section. They have a lot of sugar. So is chocolate unhealthy too? And boom, like magically the robot seems intelligent and seems like it's learning. It ends up being that after we teach the robot about like 5 foods, then it can sort of guess the other 15 foods that remain. But it all depends on how good the training set is. So I don't use the words training set with a 5-year-old, but the idea is still the same. It's like, so we only told it about these 5 foods and it learned about these 15 foods. Like, what if all the 5 foods have been good? Would it do a good job? What if they were all bad? Would that do a good job? And they can start to see how the robot needs certain examples of certain quality. Like if we only teach it about red foods and we ask it about blue foods, it's probably going to be a bit confused because like you haven't given it a good enough training set. So that one's usually really fun. And then again, of course, children want to trick the robot. It's like, well, I like chocolate, so I'm putting chocolate in the good side. And like, okay, well, we can do that, of course. How does that impact the robot? And then we can discuss that as well. And then the last activity is generative AI. And this was one that I thought was really important because AI doesn't just follow rules and it doesn't just classify things and make rules. Sometimes it is creative and it can be used in art. This particular activity is about music. So first children give the robot parameters about different emotions and how they would sound as music. So happy music sounds, kind of fast and upbeat, and it also sort of goes up in chord progression. So like rather than going like dun dun dun, it's going to go up dun dun dun. So they teach the robot that by sliding these 2 bars, like chord progression up and music fast, and then they do sad, and they're like chord progression down, music maybe a little bit slow, and then excited. So chord progression up, music fast, or scared, chord progression down, but music fast. And they teach the robot about what different emotions should sound like as songs. And then I drive all the teachers in the room crazy. And we start playing music with the robots. So children have this piano where they can play a song. And then the robot will take whatever song they make and it will remix it according to the different emotions. So it's just like really noisy, but a lot of fun. Is like children are like, playing songs and hearing the robot play their song back and sort of like going back and forth with this turn taking. And then, we ask questions like, so did the robot's song sound like your song? So if you tell it not to change anything, yes. If you tell it to go faster, it'll just change the progression a little bit. If you tell it to go slower, it'll make it a bit slower. Sometimes it'll add new notes if you tell the chord progression to go up, but you play it down chord progression. And then how does that impact the emotions? It's like, oh, well, it seems like it's kind of picking randomly, but all the happy songs kind of start to sound the same. So it's really cool to watch children sort of do this less structured, like, it's not right, wrong answer. It's how does it sound? And they're making music. And then they get up and they play a class orchestra. And then we turn the tablets off for the rest of the activity after all of that stimulation. Yeah.
So To be clear in this third concept, how are you getting at the AI element of what's happening?
So examples of this AI come up, like if you look at some of Google's AI experiments, they have this piano where you can play music along with a computer. But the question is, how does that computer know what to play? And so in this activity, children are actually setting parameters for how the computer should change the song to make it sound a particular way. So if they give the robot rather an input with three notes, C, D, E, and they tell it to make it faster and happier, then the robot should return something according to the parameters faster, and maybe it'll go up C, E, G, like even higher than the child's input. So they start to see how they can use AI to create new things.
And then you mentioned previously some of the surveys you did before and after. Was that before and after children go through this curriculum? Are there additional observations that you made about their experiences and what they've learned having gone through this curriculum beyond what we've already talked about?
Yeah. So there was the before and after about how children feel about AI and about robots. I also did a before and after about how children feel about engineers. So one of my, I guess, pet peeves as an engineer is that, there's a lot of emphasis on science and mathematics and STEM, but often technology and engineering is a lot harder to do, and so it gets less attention. So as I went through the curriculum, I was hoping that children would have a better sense of what engineers do and why engineering is fun. And unfortunately, they didn't. And I think that, a lot of that is because it was a very new concept to them. So to tell a hilarious story, the first day that I went in, I was like, okay, who here knows what an engineer is? And, in this classroom of 20, like 2 children raised their hand. And I was like, okay, that's not good. We have to do better than that. And so I, pointed to one of the children and I said, okay, you tell me, what is an engineer? Tell us all. And he's like, an engineer is someone who drives a train. And I was like, oh no, like we're really, really far further than I even thought we were. So, part of doing this research that I find, like personally enjoyable is that I get to say, well, I'm an engineer. I'm an engineer because I build things and I build things to help people, and starting to have children, think about that as a different new career path. I kind of wish going back that I had built more of that into this curriculum that I built. So, these activities were fun and they were playing games, but at the end of the day, they didn't get to see how the things they were building could be useful or how they could help other people or how they could bring joy to other people. Mm. And I think that's why, at the end, when I was like, okay, who wants to be an engineer? I still got crickets, because it's like, all right, we need to do a better job of helping children sort of like see themselves as this, but also see the value of it in society. And then also just, like I said, I did a sort of AI assessment. So how much did children learn about these things? The AI assessment was like 10 questions, all about the different activities. And some of them were kind of tricky. It was like, I think I mentioned before, if you only teach the robot about good foods, where will it think chocolate goes? For a 5-year-old, they're like, of course, everyone knows chocolate's unhealthy, but it's very difficult for them to see, like, okay, wait, but this AI algorithm only knows foods that I've taught it, only foods that I've labeled, so it'll always use those labels to make its guesses. So it was really cool to see, like, a lot of children start to get those things right, because it kind of, like, blew the developmental psychology literature, out of the water. They were like, I'm not sure if children could do this kind of reasoning yet. And I'm like, no, they did it. It was awesome.
That's fantastic.
Yeah. Anyways, 10 questions. Some of them a bit tricky. And I think the median score was like 70%. Obviously we shouldn't assess children too heavily. That's probably not healthy for them, but they understood a good amount of what was presented in front of them. And I think that's really encouraging and important. The same with like early computer science education. It was very easy to say children can't understand this, it's too complex, but the way that something is designed, it can be made accessible to children. So, right now I'm working on a deep reinforcement learning activity. So pretty much we're going to build agents that can play Snake. So first we're going to hand code it, and then we're going to use a simple neural net where we like give it a bunch of examples and then we're going to have it do deep learning. And I'm feeling very confident that the children can understand it because, if you just are able to break something down enough, they can get it.
Wow.
So if you're a deep RL person, I'm going to have some 5-year-olds coming for your job pretty soon. So get ready.
Nice. This is awesome work. Where do you go from here? So this was really the center of your master's thesis.
Yeah.
Where do you see it going beyond that?
There's so many different things that I want to do, and so much work to be done. So some really things that are going on. There are others in my lab who I was kind of like the person to go and try this and see if it worked or not. So now that it works, other people in my lab are also trying out their own experiments. One of my lab mates, Athena, is doing this work around, when children are learning with AI, how can that impact their creativity? So they're not just learning about AI anymore, they're also learning to be more creative and to be explorative as they're learning, which will have like huge benefits for them, beyond just learning a particular skill. Another student in my group, Blakely, not student in my group, like I'm their professor. Another one of my lab mates, Blakely, is working on an AI ethics curriculum. So really helping children be able to understand the ethics behind every AI decision so that they can critically evaluate the things that are around them. But also when they're building things, why teach children to build something if they don't know how to build it ethically? Like at the same time, they should be thinking about both of these things. So I'm really excited about that work. Personally, I've gotten a lot of feedback from teachers like, this is great. I have no idea about anything with AI, so can you teach me? So I'm trying to figure out the problem of how can we actually make this something that teachers can like use and feel empowered to use and not scared of, so that it can really get into classrooms and get into the spaces in Baltimore that I used to work in. And then I think also just making more cool activities. Like, in my dream of dreams, this will become like this big online platform and children everywhere can learn about AI in ways that are meaningful to them. So, there has to be a lot more content behind it. Beyond these 3 activities, what other things can children learn and what are other metaphors that make sense for them, right? Mm-hmm. So, yeah, that's all the things I'm going to do before I finish my PhD somehow. Yeah.
Awesome. And are there things that you have identified that you need? Meaning if there's, some potential partner out there that, someone in our listening community might, be connected to, anything come to mind in that regard?
I mean, yes, if I can put a plug for things. So I think one thing that would be really awesome is to have an AI person, someone who feels comfortable with AI, who's really passionate about teaching this, who I can sort of help get started with their own activities. So I'm doing that with teachers right now. And I think the biggest problem is that they're not comfortable with AI and there's a lot of work that I have to do to get them there. So I'm wondering how might it be different if I take an AI person and start to give them tools to be teachers? That would be really cool. Also, if you kind of just want to try things out with your kids and experiment and ask questions. Some of the papers that are linked in the website that we have actual AI resources that parents can go on and try right now. Just like short activities based on Scratch. So unfortunately, you have to have a kid between the ages of 7 or maybe older. But there are already things that exist that people can try that I highly recommend them try and give us feedback on.
Well, Randi, thanks so much for taking the time to share what you're working on with us. It's really cool stuff. And I'm looking forward to seeing how it evolves.
Yeah, thank you. I really appreciate the opportunity.
Thanks. All right, everyone, that's our show for today. For more information on Randi or any of the topics covered in this show, visit TWiMLAI.com/talk/225. For more information on the Black in AI series, visit TWiMLAI.com/BlackInAI19. As always, thanks so much for listening and catch you next time.